So with all of these in play and all of these kind of discussed and debated, now we get down to, okay, if we do all of these things, if we gravity correct, if we only use our data when we've got a constant angular velocity, that is, we're in that true isokinetic phase, if we align the participant correctly, that is, we get alignment of the axis of rotation, we get parallel alignment in terms of the lever arm and the limb. If all of those are taken into account, how valid and how reliable is isokinetic dynamometry? Well, we'll start here. So this is some data using interclass correlations. And what we've got is we've got data for the dominant and the non-dominant. And we've got peak torque per kilogram of body weight, it's percentage, total work, and then the average power. And what they've done is they've used interclass correlations. They're slightly different to a Spearman's or a Pearson's, but they allow us, they're one way of assessing reliability. But the rules are the same in terms of what we understand, that the closer that number is to 1, then the more reliable the data is, the kind of the greater the inverted commas the correlation. And what we'll notice is if you look at the majority of this data in the non-dominant, they're all very, very close to 1. I mean, these two here are outstandingly close. When we look at the non-dominant for both the quadriceps and the hamstrings, the peak torque percentage of body weight actually shows relatively poor reliability in the quadriceps and in the hamstrings. So it does suggest that peak torque may be less reliable. In this example, we have to think, well, why would peak torque be effective? Well, of course, peak torque is what it is. It is the highest force that's being produced. Well, it would be the highest force that's being produced in this phase here. So you then get down to, well, is it one data point? Well, what is it? So if you're working at, say, 60 degrees per second, is it over 1 second? Well, that seems remarkably short time period to take the peak torque. So you have to think very carefully about what the sampling rate is that you're going to use to make the calculation. Most dynamometers work at around about 100 hertz, so 100 samples per second. So do you average over 1 second? What happens if it's not 1 second in the isokinetic phase, for example? Or do you just take a single data point? How are you going to work out the peak? And that will therefore have ramifications in terms of the reliability in the data. If it is simply just a single value that you've taken, then it may well just be an errant data point, which will affect the outcome. So understanding how you take that data and treat it is really, really important. So let's go a stage further. Quite a big data set here. It's using the Cybex, it's using the same dynamometer that we have in our laboratory here in Cambridge. And again, this is peak torque. So this is all peak torque data. And what they've done is they've done it over 3 days. And they've got what's called a main effect. They've got interclass correlations. And they've got confidence intervals. So let's have a little look. Remember that fundamentally, that the key variable is to understand whether the data is showing any kind of differences in terms of what is going on. So if we look here, we've got these here. Look at these here. If we take these two here, this concentric hamstring, right, at 60 degrees and 120, 137, 146, 149, 118, 129, 129. So it's telling us, despite the fact that the ICC looks relatively high, can you see that there is perhaps an inconsistency here in the data when we compare the first trial to the latter 2 trials in terms of days 1 compared to days 2 and 3. The same here. When we look at this one here, which is 180 degrees per second, 106, 111, 112. So it seems to be that there is some issue of reliability or repeatability in the peak torque. In this example, in the hamstrings on the right. We see the same thing here in the quadriceps on the left at 180 degrees per second. And then when we go down to the data down here, if you look at all of these are showing inconsistencies. And we look at these, they're all less than 0.05 statistically. 133, 142, 138, 21, 29, 27, 08, 14, 11, 158, 169, 167. So it's suggesting to us that we're getting quite a lot of disparity when we're looking at peak values. Remember, a lot of this may come down to the way in which you calculated the peak. But you'll also notice that the disparity seems to be both at slow concentric speeds, high concentric speeds, and also under eccentric loading. In other words, we're seeing it. It's almost irrelevant whether it's left or right side, because what we need is to know whether it's dominant or non-dominant, which wasn't reported. But it seems to be that it's not just at slow speeds or fast speeds, it seems to be across the range of speeds that we see the inconsistency in the peak torque data. What happens though if we take the average data? Same group, same data set, and notice now there are only 2 examples where the average torque shows an inconsistency. Concentric hamstrings right, 132, 140, 134. So there's clearly some variability in the data here. And then hamstrings left, 60 degrees per second, 145, 152, 145. So, and again, if you look, both of those are the ones which are less than 0.05. Oh, sorry, there is this one here as well, which is the concentric at 120 as well. They're the only ones where we've got significant differences in the data, less than 0.05. Much, much more reliable when we're using average data. And when we take the average data, we're averaging the data across this phase here. So it would be the average across here, and you would then average it across your 3 trials. Remember, we said that you do a minimum of 3 trials, you do 5 trials in total, discard the first, discard the 5th, and then average across the next 3 trials. Now, if we then consider this a little bit more, here we've got where, and it doesn't really matter between males and females per se, what we've got here is, this is peak torque data, and what you can see, they've got this for abduction and adduction, internal and external rotation. And if we look at the data, you can see that there is some inconsistencies. The abduction for females, 37.6 session 1, 41.1 session 2, 66.7 for the males, and 70.5 for the 70.5 for the males, so we get across session 1, session 2. So there is a little bit of inconsistency in some of this data, but this comes to a head when we take the Bland-Altman plot, which is to the right, which may be a better way of describing what is going on. So on the Bland-Altman plot, we've got our mean torque across 2 trials here, and then what we've got is we've got the difference in the measurements within all the participants. So remember that the key to understanding Bland-Altman and limits of agreement is, 1, you need to know the bias score. So the bias score is quite simply the mean of the differences. What is the mean of the differences for the group? So in this example, it's difficult to know, but it's around about probably 1 or 2 Newton meters in terms of the torque. But the second thing we need to understand is, what is the spread of the data? So the 95% confidence intervals. And that kind of shows us how widely spread the data is. Remember, this is a test-retest scenario. So it goes from around about, what's this, a negative 12 as an example, to probably a positive 15. So there's a 27 Newton meter difference. So it's quite a large spread of the data. Now, is that important? Well, it's important because it tells us there's a lot of variability. If that range had been, say, 5 or 6 or 7, you could see that the data would have much less variability. The second thing is to notice how many people sit outside of the confidence intervals. So it really tells us that when we're working with the data, we have to be fully cognizant of it's much less reliable when we use peak torque data than when we use mean data. So you have to be very careful analysing peak, and it comes back to what I was saying earlier on in terms of being very clear on what your sampling interval is in terms that you're going to use when working with this kind of data.